Good evening and welcome to this webinar series by IITACB. And today we have Professor Renu Malhotra. She's a Regents Professor and Louise Foucar Marshall Science Research Professor at the Lunar and Planetary Laboratory, the University of Arizona, Tucson. And she's going to talk about mysteries of gap and pileups at planetary resonances. So the orbital spacings of planets and long-term stability of the planetary systems are quite interesting and fascinating at the same time. And to me, it's a mystery. So let's hear Professor Renu, who's going to talk more about these mysteries as she attempts to relate our current understanding of the origins of gaps and pileups that are observed at planetary resonances. So we have as moderator Professor Annapurni Subramaniam, who's the director of the Indian Institute of Astrophysics, Bangalore, and she also works in similar areas like star clusters, stellar evolution, and population in galaxies, and Magellanic clouds. And she was also awarded with Vigyan Shri Award under the Rashtriya Vigyan Puraskar this year in 2024. So over to you, Professor Renu. Yeah.
Thank you, Suju. Trying to share here. Okay, got it. And thank you, everybody, for being here. As Suju said, I'm going to talk about this topic, the mysteries of gaps and pileups at planetary resonances. So planetary resonances are ubiquitous in planetary systems. In the solar system, amongst the solar system planets, in the asteroid belt, in the Kuiper belt, amongst the systems of moons around the giant planets, as well as in other planetary systems. And for a long time, ever since at least Kepler's time, there's been this question, why are there some resonances that are important in planetary systems? Why do they exist? And later on, we also found amongst things like the asteroid belt and the Kuiper belt, there are gaps and pileups at different resonances. And so this has been an abiding question in celestial mechanics. So what my plan is to first go through some examples that we find in nature, in the solar system and in exoplanetary systems, as well as other contexts. And then we'll have a break. And then I'll continue with some of the theoretical underpinnings of our current understanding of this question. So here's a very dramatic picture of the moons of Saturn, actually the rings of Saturn and the embedded moons inside the rings. This is a picture from the Cassini spacecraft that was launched a long time ago and took these really high resolution pictures. And what you see here is lots of structure in the rings. And on the top of this image, you'll see some letters and numbers, and those are indicating the orbital resonances, the period ratios. So for example, 5:3 period ratio between between the orbital period of a ring particle and a moon. And so some places you see that it's dark, which is gaps, and other places you see bright signatures, and those are pileups at resonances. And there's lots of structure in between resonant locations as well. This has been a very long-standing question, and understanding this has been very hard to come by. We have theories to understand some of this, but not all of it. The moons of Saturn amongst themselves, the larger moons, also have lots of resonances amongst them. So for example, Tethys and Mimas are in a ratio of 1:2 in their orbital periods. Dione and Enceladus, Hyperion and Titan, a different ratio, 3:4. And it's actually all of Saturn's moons are in some, almost all of them are in some resonant ratio with each other. There's also, we'll come back to this later. A friend of mine, Dan Tamayo, put all the resonances of one of the moons of Saturn, Janus, translated them into an audio file. And we'll listen to that later on towards the end of the seminar. So one of the first observations that was recognized of orbital resonances was the very first moon system that was discovered by Galileo. And this is called the Laplace resonance. Laplace was the one who identified the underpinnings, the physical underpinnings of this resonance. And these are the moons of Jupiter. So when Galileo first pointed his telescope to the sky, and one of the most important discoveries, consequential discoveries for subsequent science and society, was the discovery that there are moons orbiting Jupiter. And that was the first evidence that the Earth was not the center of the universe. Not everything revolves around the Earth. Not everything in the cosmos revolves around the Earth. Because previously we had models that accounted for all the motions of astronomical objects as rotating, as revolving around the Earth. But here was something, a system where celestial objects were orbiting another planet, Jupiter, another object, not Earth. And this was very evident in Galileo's observations. And the most astonishing thing is that these three moons, the three innermost large moons of Jupiter, Io, Europa, and Ganymede, they are in this resonant ratio. Their orbital periods are in a ratio of 1 to 2 to 4. Okay, so it's a chain of resonances. And it's very dramatic. Even an amateur astronomer can do observations over a span of a week, say, and notice this, because you see these moons appear on one side of Jupiter, the other side, and you can see how the pattern is amongst these three moons. There are other moons in the Jovian system that are not locked in such a chain. So the next one, for example, the next farther big moon called Callisto is not in a resonant ratio. So there's a mystery that there's a subset of these moons are in a resonant ratio and not all of them are. One of my favorite systems is the Pluto system. And Pluto has this large moon called Charon, but also has a retinue of smaller moons that were discovered only in the last decade or so, couple decades maybe, since the New Horizons space mission was launched. And we started taking a closer look at this very distant system. And we have these additional moons that were discovered, Nix, Styx, Kerberos, and Hydra. And they are in a chain of near resonances in that ratio that you see there, 1 to 3 to 4 to 5 to 6. Quite fascinating, not quite a clockwork. They are near resonances, so they drift a little bit relative to those exact ratios, but quite fascinating dynamics nevertheless. In the asteroid belt, we've known for a long time that the distribution of the orbital periods of the asteroids they have gaps and pileups. So here what you see is a graph of the semi-major axis of the orbit. And you might remember from Kepler's laws that the semi-major axis of the elliptical orbit is related to the orbital period. So semi-major axis to the 3/2 power is proportional to the orbital period, actually inversely proportional to the orbital period. Or did I say that wrong? Yeah, it's proportional to the orbital period. And what you see here is semi-major axis versus the eccentricity of the orbits. And these are about 1 million asteroids that we know now. And it's obvious that there are some gaps and there are some overdensities in different places. Jupiter's location is here on the right-hand end of this graph at about 5.2 astronomical units. An astronomical unit is the mean distance of the Earth from the sun. So Jupiter is a little more than 5 astronomical units. And you can see that there's a whole group of asteroids called the Jupiter Trojans that orbit in 1-1 resonance with Jupiter. They have the same orbital period as Jupiter, but they lag or precede Jupiter in its orbit. And then you see closer in at approximately 4 astronomical units, you see a group that's called the Hilda asteroids, and their orbital periods are 2/3 that of Jupiter, and so on. So there are these gaps at some resonances and pileups, extra relative to the neighborhood density of asteroids. We'll come to a little more detail on these later on. This is a graph of just showing in a top-down view of the locations of the Hilda group of asteroids, which are we call it the 3-2 mean motion resonance. Their orbital frequency or their angular rate of motion is faster than Jupiter by exactly a ratio of 3/2. And you can see that in the sky, if you look top down, well, not in the sky, if you were to look top down on the solar system, you see Jupiter marked here near the bottom of this graph. And then you see the circle, which is the average orbit radius of the Hilda group. And the Hilda group their instantaneous positions make this pattern, this triangular pattern. So they kind of pile up at the corners, at the vertices of that triangle and spread out in between. And this whole pattern rotates as Jupiter goes around, keeping this pattern with Jupiter, although the individual asteroids will move in an elliptical orbit, okay? Just like all objects in the solar system move in elliptical orbits. But they'll go back and forth individually, but as a group, they maintain this pattern. This is not all the Hilda asteroids, because that would be too many. I marked only the brighter ones, the bigger ones, as of a few years ago. And then here in the Kuiper Belt is the analog of the asteroid belt beyond the orbit of Neptune. And here again, I'm showing the same major axis versus the eccentricity of the orbits. And you can see these pileups at orbital resonances with Neptune. So Neptune is at 30 astronomical units. You see that on the left, near the left of this graph. And you see that there's a vertical structure, which is the Neptune Trojans. They're informally called the Neptune Trojans. They orbit in the same orbit as Neptune, but again, lagging and trailing Neptune's location at plus minus 60 degrees from Neptune's location in longitude. And then you see that there are pileups at all of these other resonant ratios, the 4-3, 3-2. As we go farther out, the orbital period ratios, of course, get larger because these objects have larger orbital periods. And you see there's a very prominent pileup at the 3-2 resonance. This is the same resonance that Pluto lives in. Pluto's orbit is one of these dots here is actually Pluto. And so forth. So as we go farther out, there are fewer and fewer dots, and that's because of observational incompleteness. These objects are fainter. Not many of them have been discovered. I think maybe roughly 1% of all objects that are bigger than 100 kilometers in size have been discovered so far. So we have very sparse information about the Kuiper Belt, but enough to see these patterns, these pileups and gaps. So there are there's a huge gap between that 1-1 and the 4-3. We don't see much in there. And then farther out, there's higher density. In exoplanetary systems, so in the last, since the discovery of the first exoplanetary system in the early 1990s, we've accumulated data on about 4,000 planetary systems around other stars, nearby stars. And this is a compilation of maybe about a third of those, going back to about 10 years ago with data from the Kepler spacecraft. And if you look at the period ratios in systems where there's more than one planet that has been detected, if you look at the period ratios, there's some interesting features that we find. So this is a graph of the number of systems against their period ratio of the outer planet to the inner planet. And we see this peak, you can see this peak near the 3-2 ratio of period ratios. And there's actually a dip, strong dip near the 2-1 on one side and a peak on the other side. And here in between is actually a similar peak trough structure near a 5-3 resonance. And then there are other more distant resonant ratios as well. With a background, with a smoothish background, which looks like a a kind of a bell curve. Okay, so around or on top of that smooth background of period ratios, there's this structure. So these are resonant ratios or near resonant ratios, and they've been actually really useful. That there are lots of systems near these resonant ratios. Those orbital resonances are especially important and useful in determining the masses of the planets, because otherwise we don't know the masses. All we know is that they exist. We know their orbital periods. We know something about with these transit measurements that we do, where we measure how long or how deep the transit is as the planet transits the disk of the star. We can get an estimate of the relative size of the planet to the star, but not the mass. So when we find planets or planet pairs that are near resonances, their mutual gravity can help us determine their masses. So that's been a very important practical application of orbital resonances. So orbital resonances are also really useful in spacecraft trajectory design. There are low thrust options that orbital resonances make available as opposed to non-resonant configurations. So this is a picture of roughly, I think it was in the design phase, designing the TESS mission. The TESS is a transit exoplanet mission that was launched in order to look at nearby stars and look for these transits of planets around them, so exoplanets. And the spacecraft was launched in such a way that it took advantage of an orbital resonance with the moon, the Earth's moon, and it took advantage of that resonance and used less fuel to get into its final orbit. And that resonance is shown here. It's a 2-to-1 resonance with the moon's orbit. So the orbit period of this spacecraft is half the orbital period of the moon. It is a very elliptical orbit. And not only is it this ratio, orbital period ratio with the moon, there's a three-dimensional aspect to this resonance, which is called the VZLK resonance. I probably won't have time to go into that, but this is this makes for a three-dimensional pattern in space relative to the moon's orbit. And you can see this interesting shape here in the bottom right. So that makes for a really easier, low fuel way of getting spacecraft into stable orbits. There's a little bit of station keeping needed. You need some fuel to keep it in this, and that's because some resonances are stable. This one is not actually that stable. So to keep the spacecraft in that resonance for a long time, you need to do a little bit of use a little bit of fuel to keep it staying in that resonance. Here's another example, an example in nature that was observed over many decades, actually 2 or 3 decades. This is a comet called Comet Oterma, and this comet was observed in 1980. Here you can see this its position at this location. And prior to that, in 1910, it was observed in a different orbit. So what this is showing is a top-down view of the track of this comet over these many, many decades. So it was initially observed in 1910. It was observed to do this path. Now this path doesn't look elliptical because we're actually showing this in a rotating frame. In an inertial frame or in a heliocentric frame, it is actually an elliptical orbit, but the ellipticity of the orbit and its orientation changes over this time span. And if you look at it in this frame where Jupiter is stationary, so the frame itself is rotating with Jupiter, it makes this pretty pattern where initially it was in this sort of figure 8 pattern, which is, I think it was a 2-to-1 exterior resonance. So it's in a ratio of 2-to-1 with Jupiter. And then at some point it transferred to an inner orbit, which is this pattern, this triangular pattern that we saw before. This is like those Hilda asteroids. So it went into an orbit that was in a period 2/3 of Jupiter, and then it transitioned back into an orbit that's outside of Jupiter's orbit. So this region around Jupiter, it's called a transit region, And many natural bodies actually take advantage of this and do this kind of transport. So these orbital resonances actually become are a source of transport properties, natural transport properties in planetary systems. Okay, so I'm going to wind up. So these are the examples I wanted to share. And here I am showing you something that I picked up from Stack Exchange. It's about this question, why are some resonances stable and others are unstable? And so this person is asking, recently I've become more interested in the topic of the stability of planetary systems. I've been reading about it. It seems that orbital resonances play an important role in the stability of the solar system, as well as in the moons of Jupiter and other planets. I first thought that the orbital resonance is somehow more stable, and so we have many cases of such resonances in the solar system. But as I kept reading, I found out that in the asteroid belt, there are gaps, precisely where the resonances happen. So the resonances are actually unstable for asteroids. I then thought some resonances are stable while others are unstable. But some of the resonances that make gaps in the asteroid belt are actually present between planets. They're stable amongst other parts of the solar system. So I'm completely lost. Why are resonances sometimes stable, sometimes unstable? What am I missing? So you can kind of feel this person's pain, okay? Wants to understand this mystery. And so the answer, also in Stack Exchange, there's a pretty good answer, pretty solid answer. This is actually, so the answer this person gave this is actually a very subtle question. When I was in graduate school, I routinely asked this question of visiting dynamicists and invariably got different answers. So the gist of this person's answer is the very basic answer is that if you have two sufficiently close resonances or resonances that are sufficiently close, then each of those resonances actually becomes unstable. Otherwise, if the resonance is far from other resonances, then it's stable. And what determines this is what is sufficiently strong. What does it mean to say a resonance is sufficiently strong? And what does it mean to say that it's sufficiently close? And things get complicated pretty quickly. So there's a criterion known as the Chirikov criterion that's used to understand whether resonances are strong and sufficiently close or not. And however, this is not universally valid. So it's a very deep question in celestial mechanics. The longest running question has been, is the solar system stable? Because the gravity amongst the planets themselves produce the effects of these resonances on the planets. So Isaac Newton, from the time of at least Isaac Newton, we've been pondering this question, is the entire solar system stable under the gravitational perturbations of planets on each other? And the answer is actually very complicated. But I'll try to simplify this for you today. And we can take a break at this point. So I think maybe I'll say that the answer, there is not a universal answer, but I'll break it down to you about what we understand today. So shall we take a break now?
Yeah. So, Renu, that is a very interesting topic on, understanding. We know that there is rings around material around Saturn, but then how they're distributed, and there are patterns on that, and then resonances play a major role, and this pile up and making gaps as well. So, could you just explain why there is a resonance to begin with? Right. So there is a distribution of matter around the planetary. When the planets are formed, there's a leftover material, or is it because something is broken up? Is it the material there? And then a simple case of resonance. Is it same thing like we see in a musical instrument when there is one, one string, when the frequency matches, it starts vibrating. Is that the same thing, or could you just break it
Yes,
down?
very much so. Yeah. So the orbital periods, if you take any single planet or any two objects orbiting each other, there's an orbital period if they're bound to each other. So for example, the moon is bound to the Earth. So the moon has an orbital period around the Earth. all the planets around the sun. So each planet has its orbital period around the sun, and that orbital period depends upon the mass of the sun. Okay? Basically, it depends upon the mass of the sun and how far away or how big the orbit is. And so we have Kepler's laws that relate the orbits to the orbital periods to their sizes. The understanding of what the orbital period, how the orbital period depends upon the masses came after Newton's law of gravity. So each planet, its distance from the sun determines its orbital period. And if the orbital periods happen to be in resonant ratios, then we have a resonance. So actually, in the solar system, most of the planets are sufficiently far from low integer period ratios. The ones that are closest are Jupiter and Saturn are fairly close to a ratio of 5:2 orbital period ratio. Uranus and Neptune are close to a 2:1 period ratio. Okay, Earth and Mars are close to a 3:2, but sufficiently far. So again, that comes down to what does it mean, sufficiently far? And are these resonances strong enough? So the smaller so for orbits that are nearly circular, the strength of the resonance is how small those integers are. So small integers are stronger, small integer ratios are stronger, and large integer ratios get weaker. Okay, so we don't have to really worry about the effects of something like 21 to 23 resonance for masses like the solar system planets, but we do have to worry about ratios like 2 to 5 for Jupiter and Saturn. Those have significant effects on the orbits. The mutual gravity gets enhanced when the orbital periods are close to small integer ratios.
All right. So, so that would also mean that in these disks or around this Saturn's disks or things like that, these smaller resonances will have a stronger effect or making a larger pileup. Is that?
That's right. Yes. Yeah, that's right. So the details we don't fully understand still, but the small we see observationally, we see in Saturn's rings that the small integer ratios produce very large gaps, or sometimes pileups, and the the big integer ratios produce smaller features, thinner features.
Yeah. So what is it? I mean, why are these important? I mean, these are very interesting, of course. I mean, dynamics wise, and if you look at the frequency of motion and then the resonance. I mean, the pileup happens because at certain integers and certain ratios, and not at all ratios, etc. But mathematically, they are quite intriguing. But physically, why should we worry? Why should we worry about understanding these? I mean, what is the motivation to look at it?
Right. So, going back in history, Isaac Newton worried about this for the rest of his life. Once he figured out the law of gravity, he was looking at. So I'll just give this as a historical explanation for why it's a story. Really, why is it important? So, Newton's law of gravity tells us that the gravitational force between two objects is related to their masses and to their distance, the distance between the two objects. So if you just take two objects like one planet and the sun, we know the answer. We know what the orbit looks like. But now if you have many objects, we have the sun and several planets, 8 planets. So the gravity amongst all these 9 bodies then is acting on these 9 bodies mutually. And so if some of those bodies happen to have orbit period ratios that are close to these small integer ratios, then the gravity, their pattern repeats in time. And so the gravitational perturbations between two planets then become much larger. Okay, they can add up coherently, just like you mentioned in a musical instrument. If you have a resonance, then you get a huge volume. Right, you get a large amplitude in the vibration, and so amongst planets, the gravity similarly produces large amplitudes of perturbations in the orbits. And so that means that planetary orbits can become unstable at resonances. But if they are perfectly aligned, then they can sustain that resonance forever in principle or for very long times. And so they can just maintain a pattern for long times. So a resonance then, a resonant ratio between planets can produce instability. And that's what Newton was worried about for many decades of his life. He left, I think, he left a lot of writings about his worries about what's going to happen to the solar system. Is the solar system only, actually there's a famous quote from him that from his conclusion was that God has to interfere from time to time to put the planets back in stable orbits because these resonances can produce instabilities.
Right. Yeah, that's very nice, interesting thing. There's a question which is written saying that is a clustering applied to galaxy distribution? I think there is no resonance happening out there, right? Because this is just a matter of gravity. Here, you need to have orbits. That gives you kind of frequencies, right? So in
Oh,
the case,
yes. In galaxies also, there are resonant effects because you have a distribution of mass, and inside, just like in Saturn's
this
rings.
is within the galaxy, but in the case of distribution of groups of galaxies, it doesn't apply, right?
No, not for groups of galaxies. Not quite, I
Within the
don't think.
galaxy, yeah, within the galaxy probably, because then you have orbits and orbital periods are there. So then probably,
Yes.
yeah, okay, got it.
I mean, there are collective effects you can expect at very early times when the mass in the entire universe is more concentrated, close, when the galaxies first formed, for example, then they might have been close together, the distances were smaller, and there were collective effects amongst galaxies. But generally, no, that's right. So in the universe as a whole, I think our current understanding is that we have pretty uniform spatial distribution of galaxies. There's not galaxy patterns.
All right.
There are clusters of galaxies, of course. So, for example, the Milky Way has satellite galaxies that orbit each other, and there are probably some near resonant effects there that people worry about. But I think the difference between the solar system and, say, galaxies orbiting each other is that the galactic orbital periods are so long that there's not a lot of time to build up resonant effects.
And there could be a dissipative, so it's not conservative. The orbits are sometimes it can lose energy and could change.
Yes, there can be collisions amongst galaxies or close encounters that produce patterns within galaxies. So those effects actually are also related to some extent to resonant effects.
Okay. Right. So maybe it's a good time to get back to your talk and listen to the rest of it.
Okay, all right. Okay, so we're done with the intermission. So why is there this complexity in orbital dynamics? So let me remind you that we call orbits Keplerian orbits after Kepler's laws, and if we just think about a pair of objects that are orbiting each other, then they're in a Keplerian orbit. And Keplerian orbits are three-dimensional objects. So the orbit actually lives in three-dimensional space. And that means that in principle, there are three frequencies along the three cardinal directions. And the frequency in each of those directions, in the case of a Keplerian orbit, happens to be the same. So if you just have a pair of objects in orbit about each other under gravity, then the time it takes for them to complete an oscillation in the x direction is the same time it takes to go in the y direction and the z direction. And but of course we are used to thinking of it as just the orbital period. So we think of these as having a single frequency. And that's because all those three frequencies in the three directions are actually equal in a Keplerian orbit in just a two-body problem. This is called the degeneracy of the Keplerian orbit, that all the three frequencies are the same. Another set of variables that we can think about for a Keplerian orbit instead of x, y, z are these angular variables. So one is the angle in the orbit. The other two tell us how the orbit is oriented. So the perihelion of the orbit, or also known as the periapse, more generally, if it's around not the sun but some other central object, then the orientation of the pericenter is this angle omega that you see here, little omega, which we measure from the axis where the orbit plane intersects the reference plane. So the XY plane, if this is our reference system, XYZ, then the orbit is oriented in such a way that it intersects the XY plane. And that intersection line, called the line of nodes, makes an angle to the X direction. And that's big omega here. It's called the longitude of ascending node. So, of course, the orbit intersects in two places. So the place where the orbit goes from below the XY plane to above the XY plane is called the ascending node. The other one is called the descending node. And so this is the geometry of an orbit. So this angle, big omega, is the longitude of ascending node. Little omega is measured in the plane of the orbit, compared to big omega is measured in the XY plane. So in the plane of the orbit, if you go from the line of nodes, from the ascending node to the pericenter, the orientation of the pericenter, that's called the argument of pericenter. And these names, longitude, argument, these are all historically derived from observational astronomy. And then the instantaneous position of the object in its orbit is another angle. It's called nu. Here it's called the true anomaly. And this is the radial distance, which changes as the object goes from pericenter to apocenter to back to pericenter. And then there's another angle that tells us about the orientation, which is this inclination angle. How much is the plane of the orbit tilted to our reference plane? So that's the inclination angle. So there are many angles. There are many variables that describe the motion of an object. So it's not only a single period, it turns out. When you have many objects orbiting the sun, many planets, these two angles move slowly. For just one pair of objects, the orientation remains fixed, but over time, this orientation slowly changes. We get precession you might have heard about the precession of the equinoxes. That's because the Earth's orbit like this, the Earth's orbit itself precesses over time. So this ascending node, descent node on the reference plane move over time, and that's a precessional motion. And the pericenter moves at a different pace, typically, and so that's a different precession rate. So we end up getting three different frequencies. One is related to the orbital frequency, and then there are these two slower frequencies called the precession frequencies. So under small perturbations, we get precession of the pericenter as well as of the orbit pole. And so a Keplerian orbit then has one fast frequency and two slow frequencies. And these small perturbations then get amplified under resonant conditions. Okay, so when two planets, two moons have orbital resonances, these precessions end up having some patterns that build on each other. And the perturbations then to the orbit size, how elliptical the orbit is, how it's oriented, all of those perturbations get enhanced when the orbital periods are in a small integer ratio. So the fundamental model to study planetary orbital resonances is called the three-body problem. The three-body problem was made popular recently with that there was a trilogy of novels written by a Chinese author and turned into a movie and a TV series. Probably many in the audience have seen that. Fascinating. That was it was actually technically a four-body problem in that setting, but the three-body problem was made famous recently in this context. It was actually a stellar three-body problem. There were three stars orbiting each other and a planet. So that the planet was actually the fourth body in that picture. So the fundamental model, the simplest model, is called the three-body problem, and there's an even more simplification of that, where there's one massive body, the central body, and the other two are smaller than the central body, and amongst the other two, one is more massive, and the third body is less massive, can even go to zero mass. That's called the restricted three-body problem. And a further simplification is that we say that we're going to consider this problem in the planar geometry, where the two orbits of the the lesser mass bodies, they're coplanar. They live in the same plane. So in this case, we have 2 degrees of freedom for the third body, for the massless body. And the two massive bodies, the sun and planet, imagine it's a sun and planet, they orbit each other in a circular orbit. So that's another simplification. So you see that I've made a lot of simplifications here to come to the least, the simplest problem that we can deal with mathematically. And that this is this restricted three-body problem. So the two massive bodies, we know their orbit. We simplify it to being a circular orbit. And the least massive body, or the zero mass body, is in an elliptical orbit. And in this picture, we have 2 degrees of freedom for the massless body. And there's one free parameter, which is the mass ratio of the smaller body of M1 over the sum of the two masses, M0, M1. So it's a one parameter system, 2 degrees of freedom. And even this model turns out to be really, really complicated in finding the solutions. We find resonances at low eccentricities of this massless body, at high eccentricities, and they have different qualities. The resonance dynamics is very, very interesting and very physically relevant when we have orbital migration. So for example, this two-body system, the two massive bodies can be migrating due to other effects, some dissipation in the system, mass loss, for example. And that can be changing. This circular orbit could be shrinking or expanding. And that affects this third body, this massless body, in very, very interesting ways. And there's been very sophisticated mathematical developments about understanding the dynamics in this. So let me explain that what is a resonance in this case. In this very simplest case, a resonance is when the period of the outer body to the inner body is in a small integer ratio. I've mentioned that already. So here's an example, a 3:2 resonance where the inner body, if our massless body happens to be inside the massive body, then in the rotating frame of the massive body, there is a resonance like this. So I showed you example of that Hilda group asteroids. They basically make this pattern in the rotating frame, and the massive body is at some fixed location in the rotating frame. It can be at these black dots that you see, any of these black dots could be the fixed location of the, say, Jupiter, or an asteroid, and then a Hilda asteroid will make this pattern in the rotating frame. And the pattern is actually the following. Over time, so no single object is going to be exactly in that resonance. But if it is it is on average in a ratio of 3:2 or 2:3, 3:2 interior ratio, then the pattern it makes is going to oscillate in the rotating frame around this triangular pattern. Okay, that's called a libration. And if it's not in resonance, if it's near the resonance but not in resonance, then that pattern is just going to drift all the way around. It's not going to oscillate. It's not going to librate. So that's the distinction between a resonance and a near resonance. A near resonance may have approximately this triangular pattern, but that pattern will drift over time, whereas an exact resonance will oscillate around this. So this is like a pendulum that's rotating versus a pendulum that's librating. So the librating pendulum becomes a model for understanding resonances. And then in phase space, so in phase space meaning position and the corresponding momentum, in this case, angular momentum, if we draw the phase space picture of a pendulum, So the angle of the pendulum can either be rotating, which means it's going continuously from 0 to 360 degrees and continuously rotating, either clockwise rotations or counterclockwise rotations. Then angle going 0 to 360 will show approximately horizontal curves in this angle and angular momentum space called the phase space or state space. And when the pendulum is oscillating, you'll have this kind of phase space where you see elliptical orbits, elliptical paths, where these are oscillations, where the angular momentum is constrained to oscillate around some central value. And a rotating pendulum can have arbitrarily large amounts of angular momentum. So in phase space, there's a separatrix that separates the phase space between oscillations and rotations. And how long does it take to go on the separatrix? The time is infinite. This is like the pendulum, the ordinary pendulum. If it's standing upside down, it can stay there infinitely long. And if you just disturb it a tiny, tiny bit, it will take a very long time to go all the way and come back to its upside down position. So that's an unstable location that's shown here at plus or minus pi, or pi being radians, or 300 or 180 degrees. So if we measure the angle from the stable position of the pendulum, the upside down pendulum is at 180 degrees, plus or minus. And that's the unstable position. And the separatrix in phase space passes through the unstable position. Its period goes to infinity. The width of this oscillation region for the ordinary pendulum is proportional to the square root of the gravitational acceleration in the Earth's gravity, or whatever gravitational field that this pendulum is oscillating in. Okay, so the width of the oscillation region. So I want you to remember that, because what that means is for orbital resonances amongst planets, the width of a resonance, or the strength of a resonance, how big the ranges over which that resonance exists, there's a finite width of a resonance. It's not just the exact period ratio. There's a range around the exact period ratio, and that it's quite a complicated function of the masses in the system. In the case of the three-body problem, it's going to depend upon the mass ratio. Actually, it's going to depend upon the masses of these two massive bodies. And it's going to depend upon how eccentric the orbit is of this asteroid. And there are other things that matter too, where this resonance is. Are we talking about a 2-to-1 resonance? Are we talking about a 21 to 23 resonance? So this becomes quite a complicated function of the parameters of the system. But still, the basic point is that there's a width of a resonance. It's not just a zero width, not exact 2-to-1 ratio. And this width is related to these parameters, and approximately goes like the square root of the strength of the perturbation, of the gravitational perturbation over here. Okay, then in the simplest model, we can draw these widths in terms of the location of the resonance. I previously showed you psi major axis versus eccentricity for the asteroid belt, for the Kuiper belt, perturbed by the perturbing planet in each case. So for the asteroid belt, it's with Jupiter. And these are the resonances interior to Jupiter's orbit. Now we are looking at psi major axis ratio with Jupiter's psi major axis ratio. And we can say for the 2-to-1, we can draw roughly the width of the resonance. Okay, so it's not at a single point in the psi major axis, it's over a width in psi major axis, or width in orbit radius, or width in orbital period. Okay, so there's some range which increases the bigger the eccentricity, but it's actually not a monotonic increase. Okay, so there's actually a saturation, it reaches a maximum width, and that's because neighboring resonances, as you increase the eccentricity, the 3-to-2 resonance is growing in width, the 2-to-1 resonance is growing in width. At some point, the widths start crushing each other. Okay, so here, for example, I'm showing you 3-to-2 at some eccentricity like 0.2, that is to say it's 20% out of round. The circular orbit is not circular, it's elliptical by about 20, it's out of round by 20%. at about that, or 30% round, these two resonances, the 3 to 2 and the 4 to 3, become next to, they start overlapping. Okay, their widths start overlapping, and that's where there's trouble, when the resonances start overlapping. So if you think back to the pendulum analogy, if the pendulum were if there's a double pendulum and the two pendulums have their own natural frequencies, and and the natural frequencies happen to be close to an integer ratio, they can perturb each other with different resonances. These are nonlinear effects. And the resonances start overlapping, and then there's trouble. It's like the pendulum is trying to keep one pattern, but it's being perturbed by another pattern, and it can't make up its mind. It goes back and forth randomly between different patterns. And that's called the resonance overlap issue. And what happens then, so here again, we can look in phase space, angle, and a corresponding effectively an angular momentum space. Here, the angular momentum is being represented by the size of the orbit, because the size of the orbit is related to the orbital frequency and thereby to the angular momentum. So we can do this kind of picture of what does the phase space look like when you're close to a resonance. So here's a 3 to 2 resonance. At this same major axis, there would be, in principle, a period ratio, which is 3 to 2 between asteroid and Jupiter. At this same major axis, there would be a period ratio of 4 to 3. So unlike that simple pendulum example I showed you, where there would be just a simple phase space showing oscillations and rotations of that pendulum motion, here now we have these two different oscillation regions which are crushing each other. Okay, so some of that libration region is overlapping with the libration region of the other resonance, and that's where you get chaos. So all these, so when we look at what's called the Poincare section, this was a technique that was invented by Henri Poincare to look at the three-body problem in just 2 dimensions of phase space. Remember, 2 degrees of freedom means 4 dimensions of phase space. Every degree of freedom has a velocity component, angular momentum or momentum component. So 2 degrees of freedom in this restricted 3-body problem for the massless body, for the asteroid, means a phase space of 4 dimensions. And there are reasons why this can be reduced to a 2-dimensional phase space by looking at cross sections in that 4-dimensional phase space. And so what you see here is this region of chaos, where the asteroid cannot stay locked to any one resonance. It will not oscillate around one resonance. Instead, it will go back and forth. It will transition. It will explore the phase space around both resonances, and actually even beyond. Okay, so I'll show you a picture of this phase space evolution. Actually, or let's see. Okay, so there's this coexistence of resonances, and each resonance appears as a chain of these islands, these oscillation islands, surrounded by a sea of chaos. Okay, and here's I animated this picture with changing energy. So if you have an asteroid that's changing its energy because there's some radiation forces or so forth, its energy surface is changing, its phase space is changing, and it's going to do a lot of chaotic motion. Most of that phase space is chaotic orbits. But there are lots of patterns in there, and that's where you can get stuck near resonances. And that's part of the story of why we find many stable resonances, but they're stable on some finite times. Okay, so these are, this is now a measure. So previously I showed you these resonance widths up to eccentricities of about 0.5. But now you can see if we calculate these, compute these with a numerical procedure, then by using those Poincare sections, we can find that these widths of these Jupiter's resonances are actually not monotonic with eccentricity. They don't just look like a bell. They find there is a maximum width, and then it shrinks. So this is the region of stable orbits, and the space in between those ends up if you're close to the resonance, ends up being, or in the neighborhood of the resonance, ends up being very, very chaotic. And beyond, or as you get closer to Jupiter's orbit, in other words, this on the on the horizontal axis, as you get closer to unity in the ratio with Jupiter, these resonances overlap more and more, and there's nothing but chaos. Okay, so all of this region becomes chaotic, whereas the farther away you are from Jupiter towards the asteroid belt, there are pockets of stability for some of those resonances. So these small integer resonances, as you get closer to Jupiter, become chaotic. The small integer resonances farther away have pockets of stability. Okay, so large-scale chaos that comes about from overlapping resonances is called fast chaos because the timescales are relatively short on considering astronomical timescales or geological timescales. So they can be on the order of hundreds of years, whereas the timescales of instability in these resonances can go to gigayears long. So you can put an asteroid here, and it will be stable for the age of the solar system. Okay, but this is not actually consistent with what we see in the asteroid belt. Okay, so I'll show you. So the simple model is actually not consistent. It tells us something, it doesn't tell us everything. So the simple model predicts that these resonances, say the 4 to 3, even the 5 to 4, which I haven't marked here, they would be stable, but we don't see anything there. There are no asteroids there. The 3 to 2 has a stable pocket. Nearby, there should be stable orbits, but we see lots of gaps around here. And instead, we see gaps at some of these resonances farther out. Okay, so what's going on? We would actually expect from that simple model for these resonances to be stable. The 2 to 1 was stable. The farther away you go from Jupiter, more stability. Instead, we see these strong gaps. They're thin, but they're gaps. Their asteroids are missing there. So the simple model does not provide a full explanation. It gets us partway there, but does not tell us everything. So what is the answer? What is the better answer? So it turns out we look at the next simplest model instead of where we had Jupiter in a circular orbit and that circular restricted three-body problem. That turns out to be an important key to the chaos that we find at those more distant resonances. So if Jupiter is if we allow that, if we recognize that Jupiter is in an elliptical orbit rather than a circular orbit, and Jupiter's orbit is not particularly far from circular, its non-circularity is just a few percent, 5%, 6% out of round, very tiny. You can barely make it out as elliptical. It turns out that on long time scales, it produces that extra degree of freedom for Jupiter produces chaos. It's at a longer time scale. It's not on a time scale of decades or centuries. It's on a time scale of millions of years. So if we do that, if we do this elliptic restricted three-body problem, still planar, still 2 degrees of freedom for the asteroid, but Jupiter now has this extra degree of freedom, then it produces slow chaos at these weak resonances, these distant resonances. So there are all these sub-resonances that are created because Jupiter has this ellipticity. And that leads to this. So this is a simulation of an asteroid near the 3 to 1 resonance, where we see a gap in the asteroid belt, but where the planar circular restricted three-body problem produces stable orbits. On long time scales, this is on the order of hundreds of thousands of years. You see that the eccentricity of the asteroid goes from being confined to small eccentricities to having these peaks, sudden spurts, where the orbit suddenly gets stretched out, okay, over a period of a few 100,000 years. And then it collapses back to a circular orbit. And then intermittently, it goes through these periods of high eccentricity. So why does that explain the gap? Okay, so the orbit is eccentric. Why does that explain these gaps? So it turns out that you need the action of other bodies in the solar system, not just Jupiter. Jupiter by itself is not explaining this. So there's actually a very sophisticated story for those gaps the 3-to-1 resonance with Jupiter is a gap, because not only that Jupiter produces this kind of chaos, but then Mars turns out to be important in this picture. So when the eccentricity has these spikes, a more eccentric orbit means that the perihelion is closer than it would be for a circular orbit. So when the perihelion gets close enough to intersect Mars orbit, Mars is at about 1.5 astronomical units. The 3-to-1 resonance is at 2.5 astronomical units on average. When the orbit becomes elliptical around the 3-to-1 resonance, then its perihelion, the asteroid is going to intersect Mars orbit. And it has a chance of having a collision with Mars or having a close encounter with Mars. And if it has a close encounter with Mars, it gets a gravity assist from Mars, and its orbit then gets even more elliptical, and it can even get knocked out of the solar system, or actually more typically for asteroids, after a close encounter, the orbit becomes so elliptical that it falls into the sun. The perihelion drops as close as the surface of the sun. So the reason we have these gaps in the asteroid belt is this combination of this chaos that's produced by Jupiter's eccentricity in a resonant orbit and the action of a planet like Mars or even Earth and the terrestrial planets. So that's a much more sophisticated and complicated answer than simply saying that the orbital period is resonant, and so the resonance makes for a big amplitude of perturbations. It actually doesn't. The amplitude of perturbations is not big enough. It is bigger than we would expect in a non-resonant case, but not big enough to produce any gaps to throw asteroids out. It's the action of this chaos from Jupiter's eccentricity plus the action of the other planets. Actually, I think I'll skip over this. There are other slow instabilities that happen on timescales of millions and tens of millions of years that affect other structure in the asteroid belt. This is one called the secular resonance. It's a very slow instability. So these are for asteroids that are near the inner edge of the asteroid belt. And nothing about Jupiter's perturbations actually explains why the asteroid belt ends where it does at its inner edge. And what you just saw in this animation was the combined action of Jupiter and Saturn in producing what's called the secular resonance. This is a resonance amongst those two small frequencies I mentioned in the Keplerian orbit, those precession frequencies. So an asteroid at the inner edge of the asteroid belt, or even somewhat interior to that, has a resonance in the slow frequencies, which resonates. So an asteroid here precesses with rates that are similar to the precession rates of Jupiter and Saturn's orbits. So Jupiter and Saturn impose on each other, their orbits precess in their pericenter locations, their ascending nodes, at rates that happen to coincide with the precession rates of asteroids at the inner edge of the asteroid belt. And that's why the asteroid belt ends where it does. Okay? Otherwise, it should have continued closer in, because the terrestrial planets are not that big to have truncated the inner asteroid belt. So there are these slow instabilities that develop from those slow frequencies of Keplerian orbits. What about the planets themselves? So in the last, I'd say 20 or 30 years, we've understood this thing about this big question that Isaac Newton grappled with, which is the stability of the planets, the planetary orbits. So it turns out that Mercury's orbit is actually chaotic on timescales of the age of the solar system. And so what this is showing here is roughly the eccentricity of, this is a numerical simulation going for 2 billion years. The solar system is about 4.5 billion years old, as best as we can estimate. So the planetary system itself collapsed or formed from a interstellar cloud of gas and dust, approximately 4.5 billion years ago. And Mercury's orbit, its orbit eccentricity varies chaotically in this range of somewhere around 0.2. And over giga-year timescales, its eccentricity can chaotically go up and down to something like 0.4, 0.5, and that's big enough to intersect the orbit of Venus, where the orbit gets so big that its aphelion gets very close to Venus. And it can chaotically then over that time scale, there's no guarantee that Mercury will not crash into Venus or have a close encounter with Venus, get its orbit scattered, we call it gravitational scattering, and fall into the sun. And that can actually wreak havoc on the entire inner solar system planets. So if there's a scattering like that between Mercury and Venus, Venus also gets perturbed, and then Venus and Earth's orbits are not so far apart, then Earth's orbit would get greatly perturbed as well. So these are possibilities in numerical simulations that we found, that this chaos amongst the planets Mercury is the most vulnerable planet that way. We know it's been around. We have some information now with the space missions that we've had pictures, images of how old the cratered surface of Mercury looks. It's been around for probably 4.5 billion years already. What we can't say for sure is if there were other planets interior to Mercury that might have existed and have been chaotically lost over the history of the solar system. But the main point I want you to take away from this is that amongst the planets, there's this slow chaos coming from these slow frequencies, resonances amongst the slow frequencies, not the orbital periods, but the precession periods of the planets. And the slow chaos can wreak havoc on a planetary system. And so probably the reason we have these spacings of the planets that we do in the old solar system that we live in now, the 4.5 giga-year old solar system, all those spacings, there could well have been material planets in those spacings that has been lost because of this chaos over the age of the solar system. Okay, so what do we understand so far? Resonance overlap generates dynamical chaos, but how exactly does it generate dynamical chaos? Is it the only way to generate dynamical chaos? And what's actually happening in those chaotic zones? And it's actually non-trivial. So this is a simulation by my friend, Aaron Rosengren. He does astrodynamics. He looks at spacecraft orbits. But he did this very nice graphic of what happens to an asteroid that gets into this chaotic orbit and ends up, this is a comet. He was looking at a comet and ends up in a chaotic orbit around Jupiter, like that comet Oterma orbit that I showed you that has been followed for a few decades. And it transitions between outer to Jupiter to inner to Jupiter through these resonant orbits. So these resonant orbits are actually connected in phase space. You saw that animation of the Poincare sections. These all resonant orbits at some level are connected to each other. And so you can see this in this graphic here. So Jupiter is on the left side of this graph, this blue graph that you see. And these are resonances exterior to Jupiter's orbit. And a comet, so there are many resonances here. This is the vertical axis is eccentricity. You saw those triangular kind of phase space. So this is the path of a single comet that goes back and forth like that comet Oterma inside and outside Jupiter's orbit. And the paths are through these phase space trajectories. And so these paths are actually connected to these through these resonant orbits. Each of these snapshots that you see, so you see this triangular one, this is the inner 3-to-2 resonance. The outer pattern that you see here is probably a 5-to-4 outer resonance. And so these resonance overlap. Literally, you can see that the path of this comet is just going. It's just taking these transitions that are connected in phase space through this transition region, which happens to be near Jupiter. But there are also transition regions elsewhere away from planets. Okay, here's on a bigger scale. So Jupiter is here. a single comet can traverse these very large distances going to in very short periods of time, actually. This is that fast chaos. Over just about a century, this comet can go from being somewhere near Jupiter, let's say here, near 5 astronomical units, eccentricity of 0.5. It can run around to 20 astronomical units, which is near, so Saturn is at 10 astronomical units, roughly. Uranus is at about 20, Neptune is at 30. So this comet can traverse this huge space across the planets through this fast chaos. Okay? And the slow chaos, the planets themselves can traverse large distances with slow chaos. So these resonances provide natural pathways for dynamical transport of matter in a planetary system. How do we generate this dynamical chaos? So I mentioned this overlapping of resonances. But each of these resonances, what that resonance overlap does, the way it generates the chaos is actually it generates secondary resonances around each resonance. So here what we're looking at is, I think this is a 5-4 resonance near Earth, maybe. I think, in a planet that's about 10 times the mass of the Earth. This was being done for exoplanets. So here's a 4-3 or maybe 5-4 resonance, and this might be, sorry, this is a 3-2, this is a 4-3 resonance, this is a 3-2 resonance. Okay, these are the primary resonances. And then because of this crushing, the proximity of these resonances, they generate these secondary resonance islands around each main resonance. And these secondary resonances, the overlap of those is what generates this chaotic motion. So when those resonances get to be on top of each other, we get this complete chaos. So it's kind of going from, a few body system dynamic to, or I should say, the regular dynamic, a stable orbit gets crushed into this chaotic sea when the resonances overlap. Okay, and that happens through these secondary resonances. Another phenomenon that's related to orbital resonances is if there are additional non-gravitational forces happening. So small bodies, for example, have radiation forces on them that make their orbits drift over time slowly. So asteroids, for example, they drift, their orbits drift because of solar radiation pressure and other effects having to do with shadowing and reflection and re-radiation of solar energy. So an asteroid, so let's look at this. This is again a ratio with Jupiter's major axis. An asteroid that's in a nearly circular orbit somewhere in between two resonances, between say the 2-1 and the 3-2 in a nearly circular orbit, its orbit will drift under radiation forces. If it drifts towards the sun, it's going to get adiabatically channeled into entering this 2-1 resonance. Or if its orbit drifts outward, and the reason, depending upon whether the asteroid is spinning in one direction, clockwise or actually pole-wise, it's spinning in the same sense as its orbital motion, or if it's spinning in the opposite sense, it will drift in opposite directions. So an asteroid can then end up going either this way or the other way, depending upon how it's spinning, and it can adiabatically get channeled and captured into these resonances. Okay, so there can be pileups and losses. If it goes towards the sun, this resonance region actually turns out to end at some eccentricity here, and then the asteroid drops into the chaotic zone that surrounds the resonance, rather than being in the stable zone. Going outside here, the asteroid would get channeled into the stable zone. Okay, so we have these channels that can push asteroids into stable orbits or into chaotic orbits. So these are called convergent and divergent paths to transport of small bodies, and that figures into this picture of where we have gaps and where we have pileups. So so divergent resonances, for example, can build up eccentricities. So there's an interesting example of a moon around Uranus, Miranda, the innermost moon of Uranus. We think it has an eccentric orbit because it was built up through passing through many resonances with a neighboring satellite called Ariel. Over time, the Miranda's orbit was drifting because of tidal influence in that case. So the moon's drift due to tides. Like our own moon is, its orbit is getting bigger over time. We can measure it. It's about 1 centimeter per year, I think. Its orbit is getting bigger and bigger. So Miranda, over its age, this would be over many, many millions of years, its orbit has drifted outward through many resonances with Ariel, and its orbit eccentricity got boosted. So otherwise, tides would generally make the orbits more and more circular over time, but these resonances pump up the eccentricity. So there was this puzzle about why this moon has this eccentric orbit, and this is our current understanding that probably this figures into its past evolution to explain these eccentric orbits. And convergent resonances produce this capture into resonance, excite the eccentricities, and there are many examples of this in nature. So we think that going back to that moon system around Jupiter that Galileo discovered, this chain of resonances between Io, Europa, and Ganymede, this chain of resonances got assembled over time under the tidal drifting of these moons. So they didn't necessarily form in these resonant orbits. They formed in some orbits that were spaced by some amount, but over time, their orbits drifted into these resonances and got captured. It's called resonance capture. And then their eccentricities get boosted while they're in these resonances. And actually, there's a very interesting effect that happens under tidal drifting that when this moon, probably many in the audience know that the moon Io around Jupiter is the most volcanically active body in the solar system. We've had spacecraft fly by and watch that volcanic activity. And that volcanic activity of Io is powered by tides and this resonance with Europa and with Ganymede. So that orbital resonance is a source of giving gravitational energy, converting that into this volcanic activity through the medium of tides. So resonances are very closely coupled with other physical effects. Here, this is one of my favorite examples. So Pluto, I mentioned earlier, Pluto has its own satellite system with many resonances amongst the satellites, but Pluto itself is in a resonance with Neptune. So Neptune is our planet, our outermost large planet at 30 astronomical units, and Pluto is in an orbit whose period is exactly 3/2 that of Neptune. So Pluto's orbital period is about 250 years. Pluto was discovered less than that period of time. So actually, we haven't even seen Pluto do the entire orbit around the sun, but we know its orbit well enough and its orbital period well enough to know for sure that it's actually in this resonance. It is actually in this libration zone of this resonance. So it's very firmly captured in this resonance. And this animation I'm going to show you is our current understanding of how it got captured. So how it got captured, our hypothesis is that Neptune actually did not form at 30 astronomical units. It formed closer in, probably close to 15 or 20 astronomical units. And then it drifted outward under the effect of what's called planetesimal driven migration. This is in the early history of the solar system. There was a lot of debris in between the planets as the planets were forming. And that debris was cleared out by the gravitational forces, these gravitational slingshot effects that scatter small bodies around planets. And that scattering produces this effect that Neptune would have drifted outward. Okay, and Jupiter actually would have drifted inward. So we have a whole understanding of how the planet's orbits changed in the late stages of planet formation. So just focusing on what happened to Neptune and the debris around Neptune. So Neptune drifted out, and Pluto necessarily did not form in the resonance. It was one of many objects that formed beyond Neptune in what we call the Kuiper belt. But when Neptune drifted out, the location of its orbital resonance drifted outward, and Pluto, which formed farther out than the 3 to 2 initial location of the 3 to 2, when Neptune's orbit period increased long enough to hit this 3 to 2 ratio with Pluto, Pluto got grabbed into this resonance along that phase-space path I was showing you previously. So Pluto got grabbed into this resonance, and then it stayed in resonance. To analogize this, it's not a perfect analogy, but when you're on a swing, when you were a kid on a swing in the playground, you pump your legs to make the swing amplitude increase. Do you know how you do that? You do that by pumping your legs at what frequency? Is it the frequency of the natural frequency of the spring? If that's what you think, you got it wrong. You actually naturally pump your swing at a frequency twice the natural frequency of the swing. Okay? You could actually do it at 3/2 or 2/3 the frequency or 3/2 the frequency and still pump up. But the most efficient one for a swing in a playground happens to be twice the frequency. And that's what you actually do when you pump up so you naturally get captured in that resonance on a swing. Okay, so in a similar or analogous manner, Pluto got captured in this resonance with Neptune, and actually not only Pluto, many Kuiper belt objects got captured, and this is a simulation that produces these peaks at resonances in the Kuiper belt and some debris in between the resonances. So these are the pileups, and so this hypothesis actually makes this prediction. And this hypothesis was made before the Kuiper belt was discovered. And so when the Kuiper belt was discovered, we actually found these pileups in these resonances. And so now this idea that the planets actually migrated in this manner in the late stages of their formation is pretty entrenched in planetary science, that our solar system planets did not form in the orbits that we see them today. There was this migration. The exact details of the migration are still under research, but big picture is that Neptune migrated outward by roughly somewhere on the order of 30% of its current orbit radius from the time that it formed, and Jupiter migrated inward by perhaps on the order of 10% of its current location. Okay, so this explains many things about Pluto that used to be mysterious. Why it's in this resonance, why its orbit is eccentric. Its orbit is very eccentric, and this drifting in this resonance over this time actually pulls the orbit into an eccentric orbit from a primordially circular orbit. Here's an animation that shows Pluto's resonance with Neptune. So Neptune in this picture is this nearly stationary. It's in the rotating frame of Neptune, so Neptune is nearly stationary here. It's wobbling because its orbit is not exactly circular. It's elliptical, so it does a little. Its rotation frequency changes a little bit in this rotating frame, and Pluto does this pattern, this oscillation pattern. You can see that its perihelion does this kind of oscillation over timescales of many thousands of orbital periods. All right. I think we are getting to the end. Let me summarize. Orbital resonances are a source of orbital stability as well as instability. There's very rich dynamics on many timescales. We have lots of phenomena in the observable phenomena in the natural world, in the solar system, as well as in exoplanets. And so the answer to this question, why are there gaps at some resonances and pileups? The answer is that it's complicated, but there is a simplification. Okay, the simplified answer that I'd like you to take away is that some resonances are stable and some are unstable, and it has to do with how close the neighboring resonances are. And the closeness is determined by how big the perturbing planet is. So in the case of the gaps in the asteroid belt, the resonances where there are gaps, those resonances are narrow enough that, and the neighbor resonances, or actually I should say, the resonances in the neighborhood are wide enough to overlap with those resonances where we produce chaos and gaps. Whereas the resonances where we see pileups, the resonance itself is strong enough, it's big enough, it's wide enough, and it's far enough from the neighboring resonances that we can see pileups there. Okay, and so this depends subtly on these mass ratios and just how far those resonances are from the sources of those resonant perturbations. So in the case of Neptune, for example, Neptune's mass is much lower than Jupiter's. So most of Neptune's resonances are not as wide as Jupiter's resonances. And so they are far enough from neighboring resonances that we get, in most cases, pileups. In the case of Jupiter's resonances, some of the strong resonances have stable phase space, and some of the weaker resonances that are farther away have not stable phase space. Okay, so the mass of Jupiter, the fact that how big the eccentricity is of Jupiter's orbit. So Jupiter's orbit is somewhat more eccentric than Neptune's orbit. And so both the eccentricity of the perturber and the mass of the perturber feed into this complication. And so I want you to take away this quantitative effect that the perturber's mass and its orbital eccentricity affect where there are gaps and where there are pileups. So we have an understanding of why there are pileups at some, why there are gaps at some, and it has to do with these two factors, mass and eccentricity. Okay, I'll end there. And let me see. Oh, yes, I was going to end with this sound effect that was done by my friend Dan Tamayo. He put Saturn's rings or some patterns of Janus into music.
I'm not able to hear the music. Is it playing?
Well, thank you, everybody, for your attention. I hope I didn't put people to sleep with this very nice lullaby.
Yeah, actually, I could not hear the music. I don't know if anybody else could hear it. I'm sorry.
Oh, you couldn't hear the
So
music. Sorry
Sheila,
about
could you
that.
hear it? Yeah, so it's maybe we can play it again towards the end. So we would.
So I'm not sure what to do about
Yeah, so I think
you're not hearing the music.
So that it was not picked up in the call as such.
Oh, really? Oh,
Yeah.
okay. All right. There is a website that anyone can go to and find that music. So should I put that in the chat here? Would that be helpful?
You could do it to everyone. I guess if you share it with everyone, the message probably that'll be there. Yeah.
Okay, I think this only goes to the panelists. So if you can share, I put it in the chat.
Yeah. Okay. Yeah, I think people can see it now. Yeah, she's
Okay. Thank you. Sorry about that.
yeah, so it's there are some questions. So I think one theme which is coming out is similar to what Newton was worried about. So is there any immediate threat? So is like, the Earth crashing into sun or moon crashing into Earth or any planets crashing into anything else because of this slow resonance or any kind of things which we understand as of now.
Sorry, what's the question?
Yeah, the question is these resonances which play over a time scale or whatever, can that cause any threat? In the sense of,
Oh, I
something
see.
moving
Yes.
closer
So,
and coming and falling in or things like that. Yeah.
right. So as best as we can tell, there's a very small chance because when resonances produce chaos, we then get into statistical mechanics. It's bordering on statistical mechanics. So we have to think about the chance. What is the chance that there will be some destabilizing path that the planets would follow and crash into the sun or into each other or scatter? And the answer is that the answer we get is based on numerical simulations. And I walked you through this example of Mercury. Mercury can become unstable on giga-year timescales. There is a small chance, I think it's estimated that there's some 1% chance. And what is the numerator and denominator of that? Getting that probability is actually kind of complicated to even explain. But it has to do with how well we know its orbital parameters, and within the range of uncertainty, our uncertainty of its orbital parameters, it's possible that over a period, over the next 3 giga-years, Mercury could take a path where its orbit becomes sufficiently eccentric that it has a close encounter with Venus. And that can actually just unravel the inner solar system. The chance of that is tiny based on how well we know the orbital parameters. It's tiny. So I wouldn't worry about it on human timescales, even human civilization timescales. There's no chance that anything terrible is happening to the solar system in terms of the planets' movements. However, we have, of course, asteroids that can hit the planets, and they do hit the planets on timescales of millions of years, on timescales of life on Earth, evolution of life on Earth. So those we understand how those happen, and we don't. So for that purpose, we need to have a complete inventory of the small bodies in the solar system. So that's the effort that's going on also to understand the sources of these asteroids that could be hazardous to our planet. I think that's a sufficient answer, perhaps.
Yeah. So one more thing is, when you talk about these asteroids coming in, could you also say that, I mean, what is the process or likely process by which the one which Earth captured this year for a couple of months, right? So how did that happen? Or does that happen also often, or
Yeah,
what is it like?
that's right. So that kind of thing seems to happen on the order of a few times per year that we get these what are called mini moons. We'll probably discover more of these as time goes on because we have bigger and bigger telescopes, and
Exoplanet.
more and more time on the sky. And so we can discover, so there are many more small ones than big ones. The big ones are rare. The small ones are typically, so far, are not a major threat because our atmosphere, they typically break up in the atmosphere, and by the time they reach the surface of the Earth, they're too small to pose a threat. But it is expected that something, on a time scale of 100 years, we can expect a number of asteroids that are big enough to cause significant harm to a population center. For example, a big city, if an asteroid, even a small asteroid hitting a big city, can create a lot of damage. So it is a measurable threat. And that's why we have these programs that are increasingly monitoring that threat.
The near-Earth objects, yeah, detection of near-Earth
Right.
objects. Yeah. So there's also a question on the connection between the resonance effects and the slingshot effects. So how are they connected, or does anything the slingshot effect use the resonance effect parameter?
Yes, that's right. Yeah, it actually does. I mentioned, I showed you those paths of that comet Oterma that basically slingshots across Jupiter, near Jupiter, and goes from one resonance to the other. So resonances are related to these slingshots that we use for spacecraft trajectories. Now, we don't have to think of it like that. A slingshot can also be thought of as simply doing a ballistic trajectory that goes very close to a planet, and then the planet's gravity modifies the path of the spacecraft. But in a mathematical sense, a slingshot is going through that same space that resonances are connected to each other in phase space.
Is there a connection between the galactic spirals and other, epicyclic orbits, which we have it and we see for stars and galaxies?
So the question is, what's the connection between spiral patterns and resonances? So spiral patterns are actually a collective phenomenon where the orbits are collectively over that spiral pattern. They are actually near resonant with each other. So the spiral pattern is actually formed by a near resonance. But it's not, so in galactic potentials, the orbits are not Keplerian. Okay, because the mass is not a point mass, the central mass is not dominant. There's plenty of mass in the disk of the galaxy that there's self-gravity. You could think of it as self-gravity modifying the Keplerian potential or the Keplerian orbits. And so the self-gravity produces this pattern, and it is, in fact, related to a resonant pattern, but in a gravitational potential rather than in a Keplerian sense.
Yeah, there's also a question on the inner edge of the truncated, inner edge truncation of the asteroid belt. So what is it got to do with is it an outcome of the secular resonance?
Yes, that's right. It is. So the secular resonance there, as I mentioned, has to do not with the orbital frequency, but with the precession frequencies of the orbits. And what happens there at the inner edge, that secular resonance, the effect of that secular resonance is to increase the orbital eccentricity. So if you put an asteroid at the inner edge of the asteroid belt, or in quite a large range, anywhere between Mars and that inner edge of the asteroid belt, if you put an asteroid there, over a time scale of about 1 million years, its orbit becomes so elliptical, just naturally because of this resonance, its orbit gets the period stays the same, but the orbit gets more and more elliptical, that its perihelion drops towards Mars, towards Earth, so it can have these scattering encounters, slingshot encounters with the planets. And then its orbit gets even bigger, and its perihelion drops to the surface of the sun. So these asteroids, basically, most of the time, they end up falling into the sun. That's what you saw in that animation. That so this is a resonance between the precession frequency of the asteroid's orbit and the precession frequency of Saturn's orbit, actually. But Saturn's orbit is precessing mainly because of the effects of Jupiter perturbing Saturn's orbit. So we've actually observed this phenomenon in the form of asteroids that are falling into the sun. We've seen asteroids actually falling into the sun. There are solar probes, solar spacecraft that watch the sun that have seen asteroids falling into the sun, and we can trace their orbits back to orbits that are near this secular resonance.
Yeah, I think these are all the questions we have, and it was a very wonderful talk and very, very fascinating, actually. Thank you, Renu. And over to Sushila.
Thank you. I can't think of a time when I have not looked up and felt and wondered what was happening up there. And today's talk was a peep into many of those, trying to help us understand many of those mysterious things that are going on there. There's clearly a very, a lot happening. I might, just to liken it with something that we all know very well on Earth, it's like the traffic in any of our Indian cities. There's just so much going on out there, just at a different scale. So today we saw in a lot of detail the idea of resonance, how planets were formed, how some became moons, perhaps, and how very dynamic things are out there. On Earth, many of these concepts play out in our daily lives, but out there are just so many more variables, which is what we realize today. So the two-body, n-body problems and so on show us exactly that. Why does this work matter? There is a whole set of reasons, and Renu talked us through a lot of those through the talk today. Small things like the design of spacecraft trajectories, the question of, is the solar system stable? What about planetary orbits and their variations? Then what is the impact on Earth and us when something like the Mercury, Venus, Earth object, the objects and the perturbations, and what if something collapses into something else, and so on. So these are all questions that are important to us. Also ideas like the dissipative forces, tides and their impact on us, and we know exactly what that is. Solar radiation. So at one level, we say, when there is a lot of aurora borealis. At another level, it does impact us in many ways that we, small and big, that we don't even know really well enough. And what about time frames? Renu said, don't worry about it, not in your lifetime, but nevertheless, we can see that there are slow chaos and fast chaos and instabilities, and many of them can wreak havoc, or in the next, maybe even in the time frame of 100 years or so, just like we had the dinosaurs disappear, we could have substantial asteroid collisions, and that may have an impact on us in some way or another. So it is not completely, forget about it. So this topic is important for us to understand. How heavenly bodies migrate into different resonances, and and how they kind of hang together. It's very interesting. Very interestingly, in music too, notes that frequency ratios of 3/2, 4/3, 6/5, 5/4, and so on are considered consonant, whereas some ratios like 7/6 or 8/7 are dissonant. So it's very interesting that in the world of the astronomical objects as well, there are these different frequency ratios that different ratios that play out as well in terms of pileups and resonances in that case, gaps in that case. So Pythagoras had said there is geometry in the humming of strings, and there is music in the spacing of spheres. And that probably is something that we heard about today. I hope that today's talk will inspire a lot of youngsters to take up the study of astronomy. You know, it's not often that we have someone like Renu who has the asteroid 6698 Malhotra named after her, and also someone like her who has been who has co-discovered a trans-Neptunian object in the Kuiper belt, who come and share so readily with us about the work that they're doing and a whole host of other issues as well. So thank you ever so much, Renu, for this. And again, Annapurni, as a scientist of such eminence, she's always readily agreed to come and present to us. Both of them have always been very open to sharing their work and an understanding of astronomy with a large audience. And I think both of them do share and do popularize science and the work that they do. So thank you. We are very, very privileged that we had you do this webinar for us today. And our audience, thank you very much for your questions and your participation. Thank you, and we look forward to our next set of webinars as well.